Let's see, I sent an email out to the class about an exam review video, which is currently posted and available on YouTube. So if you want to review your exam, but you don't have time to come in and talk to me, feel free to look at that video. It'll contain detailed solutions to each and every question on the exam. You can see items missed on Learning Suite. If you want to see your actual copy of the exam, you can come to my office. My office hours are Monday, Tuesday, Wednesday, Friday at 9 a.m. and till 9 to 10, and then other times you're welcome to send me an email and recommend a few times that work, and I'll see if one of them works for me. All right, somebody asked, why the heck am I dressed up today? As you know, I play it real casual. This morning was my organ shift at the temple, and I just didn't have time to change. I do have my casual clothes in a bag upstairs, and I will be changing into them very soon, but I didn't have time. So, all right, we have been talking about stereoisomers. We learned how to assign R and S last time, and we were looking at how you recognize whether or not things are chiral, and how do you recognize whether two molecules are enantiomers of each other. These are related questions, but the basic definition of whether or not a molecule is chiral is that molecule the same as its mirror image or not? So your fallback position is always just draw the mirror image, and then you've got to be good at manipulating the molecule on paper or with a model to convince yourself that either the mirror image is the same thing or it's not. Last time I presented to you this compound, we assigned R versus S. We drew the mirror image, and then we said that they looked like they might be enantiomers, but with a few little tricks, we demonstrated that they were actually the same thing. One manipulation you want to get used to on paper is the so-called pancake flip, where you literally flip it over with the spatula, and you could see that this molecule flipped is actually the same as this one. Another option you can do is, especially when it looks like the molecule might have some symmetry, notice that you've got 4 carbons and OH groups on carbons 2 and 3. So if carbon 2 and 3 are potentially equal by mirror symmetry, a good option is to try to draw the molecule such that the methyl groups are eclipsed with each other. And when we do that by rotating around this bond, we see that the molecule has a plane of symmetry. And a plane of symmetry in the molecule means it's automatically not chiral. And I think I demonstrated that last time by just showing that if you have a mirror plane of symmetry, you just slide it over and then the whole molecule's there. And so it is not chiral. This molecule that is not chiral we described as a particular kind of not chiral molecule. It does have stereocenters, but it is not chiral because of a plane of symmetry, so we'll call that a meso compound. Some people overgeneralize the meso term. We only use that for molecules with stereocenters that are nonetheless not chiral. Okay? All right, so then we talked about some tricks I will use. I don't know, tricks I will use or really some three-dimensional reasoning I want you to master. And I've already basically shown you one of them. I can conceal a not chiral molecule by drawing it in such a way that it looks like it might be chiral. And if you're not good at manipulating molecules in your head or on paper or with a model, you might have concluded these two are enantiomers. But the right answer would have been they are the same compound. And I might have asked, is this molecule chiral or not? And you would have looked and seen, oh, there's stereocenters. Boom, it's chiral. But if you don't know the definition of chiral and you can't manipulate molecules in your head or on paper with a model, you're going to get that wrong too. Go ahead.
So are we free to just rotate around any carbon-carbon bond that isn't in a double bond?
That's right. You are free to rotate around any carbon-carbon sigma bond. And the reason for that is that at room temperature, rotation around sigma bonds is free. Actually, if you get down really cold, you can start saying that a lot of other things are chiral because conformations are different. The idea with chirality is you can't interchange via any process that's available under the conditions you're talking about. But we're not going to worry about that. But yes, you can rotate around sigma bonds freely. And if a molecule's chiral in one conformation, it's chiral in all conformations. If it's achiral in one conformation, it's not chiral in all conformations. Go ahead.
So I'm assuming this does not apply as well to rings, I mean carbon-carbon ring.
So does it apply to ring compounds? Can you rotate? Well, yes, in the sense that you can chair flip. So I gave you this cyclohexane ring with 2 methyl groups. And we drew the mirror image, and it would be difficult from this point of view to sort of rotate things around. I mean, the way to see that these two are the same from the chair conformation is simply to do the chair flip, wherein methyl group 1 and 2 becomes an up carbon, 1 becomes a down carbon, CH3 here, oops, and CH3 here. And now, is that still, did I do that right or wrong? That's right. So now I have to sort of imagine in my head grabbing a hold of that molecule and spinning it around maybe 120 degrees, and this methyl group is going to line up with this one, this methyl group is going to line up with this one. That if you can't see that, that's okay, because you should really not try to do this problem with the chairs. You should instead draw the molecule as it's seen from above, and there it becomes obvious that this is a not chiral molecule. But yes, the way you can demonstrate that is there is rotation around carbon-carbon bonds in a 6-membered ring. Saw a hand. No? Yes? Yeah.
So the book talks about examples where you have 2 molecules that are in enantiomers, and you can switch groups, which one's forward and which one's in the back.
Yes.
And that one's a meso compound. If that meso compound is a diastereomer, is it only meso compound, or does it have the 3 stereos?
Okay, so I think the question is you can think of other ways to show stereochemistry. You can think of other stereoisomers, and what's the relationship between those? And yeah, we'll get to it. I will just say another way to draw a potential enantiomer would be to draw the molecule in the same way without drawing the mirror image. And then you would attempt to draw each and every stereocenter with opposite configuration. Only in this case, do you see how that looks like it's an enantiomer of this, but you just pancake flip it and it's the same thing? Yeah. So another way, I guess let me back up, another way you can recognize enantiomers for a simple molecule, let's see, that's no longer simple. All right. This is a chiral molecule. It is not the same as its mirror image. I could draw its enantiomer by simply drawing the mirror plane and then reflecting everything across, or I could simply draw the molecule in the same way and switch the stereocenter. Okay? So this stereocenter is R, this one is S. It would be So one way you can draw an enantiomer, or one way you can recognize enantiomers, is they will have opposite configuration at each and every stereocenter, but watch out for the meso compound. Because with the meso compound I just demonstrated last time, you've got opposite stereochemical configuration at each stereocenter, and yet they are the same molecule because of the mirror plane of symmetry. All right? So you're identifying enantiomers. Always, if you're confused, always go back. Are they mirror images of each other but are still not the same thing? Okay? Shortcut for identifying enantiomers is They'll have the opposite stereochemical configuration at each and every stereocenter, but watch out for the meso compound. All right? And I'm saying that multiple times because some of you, despite hearing it, will blunder into that on the exam. And I am sorry in advance, but I'm disclosing all my tricks up front. This is all about you developing the spatial reasoning to recognize these things. All right. So you mentioned the word diastereomer, and one question you could ask is, what if we just change one of these stereocenters? Let's stick with the cyclohexane ring and just change one of the stereocenters. But before I move on to that, what other questions do you have? Yeah?
Those two cyclohexane rings that are mirrored there, is that orange line a line of symmetry?
Yes. So this is our mirror plane. I guess I should have used... Okay.
Sorry.
Hold on. Got multiple questions at once. This is the mirror plane. Man, it's like we're back in the Zoom days and there's questions coming from the chat too. So the orange ones are mirror planes of symmetry. The black one is the mirror we're reflecting the one into.
And so, is it still symmetry even though one's axial and one's equatorial?
Yes. Is it still symmetric even though one's axial versus equatorial? Yes, because chair flipping is fine with those substituents at this temperature. Yeah. You could imagine if you can freeze one chair conformation out, then perhaps different chairs, but I can't think of a situation where that would be the case. Yeah. So yeah, it doesn't matter that one's axial versus equatorial here because we can do the chair flipping. Okay, so this was a question about, are those stereocenters? Ooh, no, we're not going to do that. Are these stereocenters? Da, 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 da. Help, let's see. Are those stereocenters? Well, it depends, because you didn't draw dashes or wedges. So let me give you this situation, and sorry. Whoa. All right. Is this a stereocenter? Is it attached to four different things? Well, yes. So we could assign R versus S. You got a secondary carbon, a tertiary carbon. So let's see. I'm just doing this fast. We don't have to, don't worry if you're not following along. This will be 3. This will be, carbon, 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 hydrogen, carbon, 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 hydrogen. Yeah, I'm not, what's the rule there? You've stumped me on terms of what the rule should be. There is, but that doesn't mean you can't assign, there is a plane of symmetry in the molecule, but that doesn't mean you can't assign stereocenters. Yeah, so what did you come up with for R versus S? You couldn't do it? Okay. That's all right. This is a program called ChemDraw. And you will hate ChemDraw because you will wish you had used it. Come on. Can you see the screen? You can see ChemDraw? Okay. So we'll just draw that system. So take comfort in the fact that if I can't solve the problem myself without help, then I'm not going to ask you to do so on the exam. But I'm interested enough in this question that I'm going to take a minute to try to resolve it, if that's okay. If not, you can complain about my egregious waste of classroom time in the end of semester reviews. At the same time, you complain about all the time I wasted coloring. All right. No? Oh, goodness. All right, well. Okay, so there's your molecule. Okay. Fine. Is that better? Okay. So I'm going to circle this. We're going to come here, structure, convert structure to name. And that doesn't help because we want to know how to number things. Let's see, where's show stereochemistry? Structure, traditionary object. Okay. So the answer is that molecule is not chiral. Are those all stereocenters? Yes. For the one on top, so actually let me just copy this down on the iPad and then we can go back to that because we're not recording the ChemDraw stuff. So R, S, little s? What is little s? Yeah, so obviously there are rules that I don't know. But you can say this molecule is definitely not chiral because of the plane of symmetry that goes right through the middle of it. So stereocenters and chirality aren't as coupled as you think. If you have one and only one stereocenter, you must be chiral. If you have more than one stereocenter, you might be chiral, but watch out for the meso compound. This here is an example, excuse me, of a meso compound. Now, I'm not sure what the rule is for assigning R versus S, because as I went out, it looked like they were going to be bonded to the same sorts of things, though you could argue that a tertiary carbon is different from a secondary carbon that's doubly bonded. So I don't know what the R versus S rule is, but accepting that as a given, if these two stereocenters are different from each other, have different configuration, then you can, in fact, assign a stereochemical configuration here because the R side will have higher priority than the S side. But I think they're calling that little s because I don't know. All right, so you've stumped me. Another fun example of that is, you didn't want to, but ha ha ha. A related example that's similar is this one. You've got R here, S here. This molecule is not chiral, but this is a stereocenter because it's different on one side versus the other, and R takes priority. So we would call this probably little r, but it's not chiral. This is sort of mind-blowing, so don't worry about this at all. Why am I spending time on it? I don't know. I can't stop. This one is chiral, but stereochemical configurations are R on both sides, and therefore the thing in the middle is not a stereocenter. Right? So this is all about demonstrating that whether or not something's a stereocenter may or may not be related to whether or not it's chiral. So your definition for a chiral molecule, fall back to it is not the same as its mirror image, and that's all. Now, shortcut is look for stereocenters, but beware if there's more than one, because you can fall into the meso trap. All right, other questions? Yeah?
Sorry, I'm a little bit confused because we defined a stereocenter as a carbon attached to 4 different things.
Yes.
Can we go back to our fun
Crazy example.
That one. I see a carbon connected to 2 carbons that if you follow those carbons along, it ends up being the same.
Yeah, technically though, because the stereochemical configuration is different, you can count them as different substituents. What? I didn't make up the rules. And I clearly don't know all the rules. Like I didn't know about the little s and the little r. But my guess is the thing that this is a little s is, yeah, you can assign a configuration there if you want to, but it doesn't matter. Okay. Right, so that was fun. And now it's done. Oh no. It just went away. Okay, that's convenient. Nope. Okay. Yeah, it's just gone. So that was all, which is fine. That was all just about illustrating that whether or not you have stereocenters is sometimes not connected with chirality. Be careful and watch for the meso compounds. All right. So let me show you one last way I can conceal a non-chiral molecule. And then we'll talk about diastereomers, because we still want to get back to the question of what happens when we change one of these stereocenters and not the other. So the third sort of secret and evil way that I can conceal molecules, whether they're chiral or not, is to draw them as a Newman projection. And this is particularly, I don't know, nefarious is maybe. And then I'll ask, is this chiral? Alternatively, I can draw 2 such molecules and say, are they enantiomers? And you can't automatically answer no, because I might be playing with you and I might actually make them real enantiomers. So you never know what's going to happen. So what do? I mean, they are mirror images of each other. If you look at how we've drawn these Newman projections, they are mirror images of each other. What's here is a reflection of what's here and vice versa. But that doesn't answer the question as to whether or not they're chiral. In order to determine whether they're chiral, you have to see, are these mirror images the same thing? So let me show you a couple of ways you can approach this problem. The first way is we're just going to stick with the Newman projection. Whoa, where did that orange line come from? That's kind of awesome. I feel like there's some, oh. Wow. Okay, hold on. It was there, except it's not. I'm really sorry about. Oh, okay. So now we got to, what we want to do is circle all of it. It's back. Ta-da. Oh man, we just need to move on. Move on from that. Okay. New page. Sorry. Oh my gosh. All right. So ClHCH3. I can't remember how I drew it, but this will work. Then we'll do the mirror image. Okay. Right, so the question is, are these even the same thing, or are they enantiomers? So one way you can approach this is to stick with the Newman projection, and you notice that the carbon in the front and the carbon in the back are both attached to similar things. So that's where the red flag wants to go up, and you want to say, hey, I could potentially have a meso compound here. So one thing you can do when you're looking to look for symmetry is try to arrange things so that the similar groups are eclipsed with each other. So I'm just going to rotate around the carbon-carbon bond such that the stuff in the front is now eclipsed with the stuff in the back. And one of the things I see is that chloro is eclipsed with chloro, methyl is eclipsed with methyl, hydrogen is eclipsed with hydrogen. I'm going to do the same thing here. I'll take the methyl group and I'll rotate it down, and we'll get this. All right. Now, you might still think that they are mirror images of each other, and they are, but when we're in this point of view, we can see that the page itself is the plane of symmetry. Okay? And that's true here on the left as well. And now you can see that if we pancake flipped our Newman projection, I think this works. Slide that spatula under there and flip the thing over pancake-wise, and the carbon in the back ends up in the front and looks like this. Okay, so that's one way you can do this. Now, Newman projections can be tricky. So one of the other options for dealing with this situation is to get out of the Newman projection. So I don't like this disappearing when we try to shrink something deal. The other thing to try to do is to get out of the Newman projection as quickly as you possibly can. So the way to do this is you got to put yourself in the plane, or you got to put yourself in the plane of the page looking towards this molecule. And I'm going to highlight in gray all of the groups that are going to be just regular straight lines. So if we lean over this way, on our right-hand side, we'll have a chloro. Then here's the bond between the two carbons. And then on our left-hand side, we'll have a hydrogen. Got that? Then I just go each carbon one by one. The carbon in the back, I've got a hydrogen coming out towards me, and I've got a methyl group going back away from me. On the carbon here, out in the front, or on my left-hand side, I've got a chloro coming out towards me and a methyl group going back away from me. Now, all I really need to do is rotate a little bit around this carbon-carbon bond. I'm going to grab a hold of this chloro group and pull it up so that it should be a wedge pointing out at me. And in so doing, this hydrogen is going to be pulled downward into the page so that I can redraw the molecule as hydrogen here, chloro here, methyl here, methyl there. Now, hopefully, you can see the symmetry plane. All right? And of course, we would need to do that again. We would need to repeat that process for the other structure. And when we do that, copy. Repeat that for the other structure. Again, I'm going to have chloro the carbons and the hydrogens in the plane. Oh, shoot. Okay, on the carbon in the back, which is on my right-hand side, the methyl group's coming out at me and the hydrogens towards the bottom. On the carbon that's in the front on the Newman projection, or on my left-hand side, I've got the methyl group coming out and the chloro going back away. And again, all I need to do at this stage is I'm going to rotate around this bond such that I bring chloro up into the plane of the page. Doing that is going to rotate the methyl group towards the bottom of the page, but still oriented outward, the hydrogen towards the bottom of the page, but oriented backwards, and the chloro group here. And again, you can see that they are, this is symmetric too, and these are the same molecule here and here, right? Oh, shoot, we're using the orange dotted line for a specific purpose, so. Okay, questions about that? Yes?
We already knew they were mirror images. As soon as we found what airplane was, it's a meso compound.
Right, that's a great point. We already knew they were mirror images. As soon as we identified one as a meso compound, the other one has to be as well. So we just exhaustively went at it from both directions. But yeah, you wouldn't have to. Another hand? No? Okay. Okay, so you're going to have to practice that. Now, we're leaving something important out. We've focused only on, is it chiral or not, and are these two enantiomers or not? So let's go back to, we're skipping over that, and what we need to do is just have some sort of disclaimer. That's sufficient, I think. No? Okay, let's try. We need a sort of deep red color. This is not. This stuff in the box is not on the test. So attested and affirmed this day by with the dripping blood in perpetuity, world without end. Okay. So, all right. I'm sorry about that. I know that some of you are thinking, why the heck are you spending time in class on stuff that's not on a test? And some of my colleagues say, I do not have enough time to tell you things that are not important. Everything I say is important. And I think this stuff is important too. Nevertheless, I feel like knowledge for itself is valuable. So I don't know. And I know you like when I spend time on things that are not going to be on the test. So I think it works out for both of us. Right, so now let's deal with the situation that was alluded to above. What if we take the dimethyl cyclohexane, but now let's change one and only one of the stereocenters. We can assign stereochemical configuration here if we want to. Let's see. This would be 1, 2, 3. This one would be R. 1, 2, 3. This one would be S. Okay. What's the relationship between these two? Well, this one is not chiral. We could draw the mirror image of the other one just to see if it is chiral. Right? And we would see here that this is S and that is S. So we would now need to play around with our spatial reasoning and try to figure out, can we ever superimpose these two? And the answer is no, you can't. This one's particularly insidious because you can try the pancake flip. Flip that over. What happens? It's just the same thing again. This is a type of symmetry called C2 symmetry. You don't need to know that, but there are molecules that you can do the pancake flip, and it's the same thing. So no, there's absolutely no way that we can make these two the same. So we're going to conclude that these are chiral. They are mirror images, and those two things put together means they are enantiomers. Now, this one is the meso compound. It doesn't have an enantiomer. It is its own enantiomer, but it's not chiral. These three are stereoisomers of each other. We're going to have, remember, the word we use for any kind of stereoisomer other than enantiomer is diastereomer. So these two are diastereomers. And these two are also diastereomers. These two are enantiomers. All right? So a diastereomer is simply a stereoisomer that is not an enantiomer. This is a concept I struggled with, and I can remember going through OChem and vaguely getting it, and then sitting in biochem, and somebody started saying something about a diastereomer, and I had no idea what the heck they were talking about. Neither did they, actually, but anyway, the best way to think of it is there's two kinds of stereoisomers. There's enantiomers and diastereomers. Enantiomers are very specific. They have to be mirror images, but not the same thing. Diastereomer is every other kind of stereoisomer. Yeah.
A stereoisomer is when the same atoms are attached to all the same atoms.
Yep, same connectivity, same molecular weight, same things attached, but different shapes, so stereoisomers. Yep. Okay, so I don't know if I'm gonna, I probably am gonna do this. Again, I had 4 sons and we grew up watching VeggieTales, and so this song applies to enantiomers and diastereomers in a way that you don't appreciate, but we'll go ahead and turn this on. I don't think we're going to hear the words. Let's see. How do we... Let's see. Audio, VeggieTales.
Really?
So how do I do audio whilst... Okay, fine. We'll have to stop the recording here. Okay, so now you can see how this can get even worse, because I could have drawn these two, and I might have instead switched the stereochemistry on one of them. And asked, what is the relationship between these two? And you would need to go through and demonstrate that they're not mirror images of each other, and they're not the same thing, and therefore they're diastereomers. Okay? So what is the relationship between these two compounds? These are diastereomers. Okay? These were not enantiomers, even though they're mirror images, they're the same thing. Okay, this is going to take some practice, and you're not going to get good at it until you make a ton of mistakes. So go start making mistakes on these kind of questions. Now, we need to sort of move on to who on earth cares. And the answer is, well, hold on. I forgot to say, diastereomers are different molecules. They have different chemical and physical properties. Enantiomers are different molecules, but they have to have the same chemical and physical properties by definition. So this has some interesting consequences in biology, because biology is composed of chiral molecules. So your proteins are made of amino acids that are linked together via amide bonds. You've seen some of these recently on an exam. Familiar? This is a stereocenter. That's chiral. And all your proteins have these stereocenters and are therefore chiral. They even have chiral shapes too. Proteins can adopt helices, which all spiral in the same direction, and that direction is governed by the stereocenter there. Your nucleic acids are chiral, right? The carbohydrate portion of your nucleic acid has stereocenters. And that determines, those stereocenters determine the twist of the DNA double helix. Now, did you notice with diastereomers that they're different in stereochemical configuration at least one, but not all stereocenters? In a way, you can broaden your definition of diastereomers to include not only molecules that have stereocenters in themselves, but also complexes of molecules with stereocenters. So suppose you have protein, Pac-Man protein, whatever, A, and suppose this is all composed of L amino acids. That's another way to talk about chirality. It's different from R versus S. Don't worry about it. But this is an L protein. It is a single enantiomer. It is a chiral molecule. Now suppose it binds a molecule that has R stereochemistry versus a molecule that has S stereochemistry. L chiral. Our L protein here, bound to the R isomer, is different. It's a diastereomer of our L protein bound to the S isomer. Two different situations, two different outcomes. We'll talk about this more next time, but what that means is two molecules that are enantiomers might have different biological effects. That's really important in drug discovery. So we'll talk about that more next time.